The first thing we want to do here is find the algebraic mean, or the average of each pair of numbers. So somebody just help me out real quick with this first pair, 2 and 8. How are we going to find the algebraic mean? Kayla?
Well, I think we can do 8 plus 2 equals 10, and then 10 divided by 2 equals 5.
Okay, so to find the algebraic mean, or the average of two numbers, you add the numbers together and divide by the number of numbers, right? So in this case, I'm going to just use a little a here to represent arithmetic mean. We would do 2 plus 8 divided by 2, and 2 plus 8 is what, Kayla? 10, and 10 divided by 2 is... Let me fix that. So we get an arithmetic mean of 5. And before we go on to the geometric mean, what does that mean? What does the 5 tell us about the 2 and the 8? Don't use the word average. Don't use arithmetic mean. What does it tell me about the 2 and the 8? Austin? Yeah, 5 is in between, but so are a lot of other numbers. Did you say it's in between? Yeah, it's the number that's in the middle, or halfway between 2 and 8. Thanks. So 5 is the number that's halfway between 2 and 8. Now, I showed this to you before. I'm going to show it to you again. Who remembers what an arithmetic sequence is?
Is that when like they all follow the same pattern to get the next one you do?
What kind of pattern?
Math.
There you go.
You plug something in
What's that?
to get the following answer.
Did you open it up? Open it up. So it is a pattern, but it's a certain kind of pattern. What kind of pattern is it? Okay, put that away.
Jake said geometric.
No, that's the other kind of pattern that we talked about.
Algebraic.
What is an arithmetic sequence is the question.
When you use a formula to find the following answer.
Can you just give us the number?
Wait, I think I got this on the tip of my tongue.
You got it right.
That is an arithmetic sequence. Why? Tiffany?
The distance between each number is the same.
Okay, yeah, exactly. So the distance or the difference between each number is the same. To go from one number to the next in this pattern, what do we do? Add 6. So an arithmetic sequence was the kind of sequence where you add the same thing over and over again to get the next number.
I didn't even notice that.
Now, here's why that applies to an arithmetic mean. 5 is the arithmetic mean of 2 and 8. If we list 2 and 8 with a space in between them, what number would go between 2 and 8 to make this an arithmetic sequence? 5.
3? He said 3?
Now, I know where that came from. The distance between the numbers would be 3, right, Miles? So what Miles was saying is you would add 3 to get each number. It wouldn't actually be 3 in between, but you would add 3 to 2 to get 5, you would add 3 to 5 to get 8, and you could continue on after that. So the arithmetic mean is the number between two other numbers in an arithmetic sequence. Okay? So using that logic, what is a geometric mean? It's the number between two numbers in a geometric sequence. What is a geometric sequence?
Jake? Didn't Jake say something? Ooh.
What am I doing, Tatiana? Multiplying by what? Yeah, we're multiplying by 3. I'm sorry, I couldn't hear what you were saying. So in a geometric sequence, we multiply by the same thing over and over again. So arithmetic sequence, we add the same thing or subtract. In a geometric, we multiply, or we could actually do what? Divide. So we either multiply or divide by the same thing over and over again in a geometric sequence. So what we're trying to find here is the number that would go between 2 and 8 in a geometric sequence. Now, this isn't as immediately obvious, I think, as the arithmetic sequence. Does anybody remember how to do this? How to find that geometric mean? What are we going to use? We're going to use a proportion. A proportion is when two ratios are equal to each other. You guys remember the means extremes products theorem? We used the means extremes products theorem. It was kind of a fancy way of saying cross multiply. So what are these two positions here called? Those are the means. Since we're trying to find the mean, I'll call it G. I'll put G there. And then anybody remember what these two are called? The extremes, here and here. And what should we put there, Kayla? 2 and 8. So we actually put the mean in the means positions. Now, we don't know what the mean is, which is why I put a variable there. I called it G because we're looking for a geometric mean. That's something that makes sense to me. Okay? How do we solve for G now? We don't cross multiply. We don't call it that. Means extremes products, right? So the product of the means is going to be what? G squared. And the product of the extremes is 16. And we'll set those equal to each other. How do you get that, Kayla? Yep. So we take the square root of both sides. We get G equals... Actually, we get two answers for G. We get G equals positive 4 or negative 4. Why does negative 4 not make sense here? William, say that again. It's not in between 2 and 8. So when we're finding a geometric mean, we're looking for a number between 2 and 8. So we get G equals 4 here, and that is the number that goes between 2 and 8 in our geometric sequence. 2 times what is 4?
2.
And then 4 times 2 is 8, and then so this geometric sequence we're multiplying by 2 over and over again. Does that make sense? Okay, so that one took a little while, but I think the rest of them should go fairly quickly, right?
Yep.
So what are the next two numbers? 6 and 12?
Oh, man.
Arithmetic mean. Who wants it? Somebody from group 1.
If it doesn't come out to be like...
We'll talk about it when we get there. Somebody from group 1. I need help.
Yeah.
Arithmetic mean.
Come on, Tatiana.
Maddie, go. Oh, hold on. Don't figure out what that is yet. Let's write the whole thing down. Hey, let me make a comment here. I already said this to somebody in here. You don't want to write something like this. Why? What's wrong with that? Oh, 2 equal signs is fine, as long as not both sides. There's actually 3 separate expressions here that should all be equal to each other if you write it like this. This equal sign right here is saying that 6 plus 12 is equal to 18 divided by 2. This equal sign right here is saying 18 divided by 2 is equal to 9. This equal sign's correct. This one is not. Because 6 plus 12 is not equal to 18 divided by 2. So don't write something out like this and say that 2 things are equal to each other and just string along a bunch of equal signs and then change it. If you're going to string along equal signs, then everything needs to be equal. Otherwise, you're not really writing down what you mean. So we'll write down everything at once to avoid that problem. 6 plus 12 is what, Maddie? Okay, and then so we have 18 divided by 2, which is 9. Good. Okay, geometric mean. I need somebody from group 2.
So I use A as a variable, so put those in my...
Use A for the geometric mean, huh?
And we already used G.
We already used A twice.
Oh.
I'm gonna keep using A and G.
Okay.
I'm gonna use A for arithmetic, G for geometric, and that way I know which one's which. I know that G stands for geometric mean. So Kayla, go ahead.
Okay. Put A in the means.
And when you said A, you meant G, right? I used A for arithmetic mean, so
Okay.
I'm going to use G for geometric mean.
Okay. And then I put 6 and the 12 in the.
Okay. And then when you do the means extremes products, what do you get?
G squared equals 72.
Okay. And is 72 a perfect square?
No.
So what do we get for G here? G is equal to the square root of 72. And what can we do with that?
6 and 12.
We can simplify that, right?
Yeah.
Let's do 6 and 12. Let's not break down that 6. Let's just leave it as a 6 and make this 6 and 2. Why would I do that?
Because it's just a product.
Yeah. When we're simplifying a square root, you don't need the prime factors if you have factors that match up. So we have a pair of 6s. There's no point in breaking those 6s down into 2 2s and 2 3s because then we're going to have 2 pairs coming out making that 6 instead of 1 pair coming out making the same 6. So it really doesn't matter as long as you have pairs. And what are we going to get when we simplify this, Kayla?
6 root 2.
6 square root of 2. That's going to be your geometric mean. Any questions about that one?
No.
All right. What is my next pair? 3 and 12? All right. So somebody in group 3, we need to find the arithmetic mean. I'm going to use A again. Brittany?
3 plus 12 divided by 2.
Okay, and what is 3 plus 12?
15.
And what is 15 divided by 2?
7.5.
Okay, 7.5. Or what's another way you could write that?
7.5.
7.5. So these three, 15 halves as an improper fraction, 7.5 as a mixed number, or 7.5 or 7 5/10 as a decimal, are all acceptable answers. I actually like this the best because it's the easiest to work with. Moving on. I like this second best because it's the second easiest to work with. Mixed numbers are really not easy to work with except in very special circumstances, so I don't like mixed numbers really at all. It's not wrong though, and I wouldn't count it wrong if you gave me that as an answer. That is an accurate answer, so it would be acceptable. So any one of those three is okay. How about geometric mean? Somebody in group 6. Go ahead, Austin.
Alright,
Thanks for volunteering.
are we doing the G still? Alright, the G and the G.
Yep.
Alright, put a 3 over one of them, and then the 12 underneath the other one.
Okay.
And then you get G squared equals 36.
Okay.
And the square root of 36 is 6, because it's like a perfect square.
Yep. That was pretty easy, right?
Yeah.
So what that means again is that 6 is the number between 3 and 12 in a geometric sequence. 3 times 2 is 6, 6 times 2 is 12. So I multiply by the same thing going from 3 to 6 as I do going from 6 to 12. Does that make sense? Okay. Last one was 10 and 15, I believe. Okay, group 5, I need an arithmetic mean. Who wants it?
Austin.
Go ahead, Austin.
10 plus 15 divided by 2.
Okay, and what is 10 plus 15?
10 plus 15 is 25. And divided by 2 is 12.5.
Okay. Or what's the other way we could write it?
25 over 2.
Okay, or
12 and a half.
any one of those three is okay. I like this one the best. I like this one the second best. I really don't like that one. So much that I put next to it. Okay, and group 4, we need the geometric mean here. Go ahead, Maya.
10 over G equals UG over 15.
Okay.
10 times 15. And no, you get G squared equals 150. And your answer is 5 over 6.
Okay, so you're jumping ahead a little bit. So we get G equals the square root of 150, and then when we simplify that, this is one that we'll actually have to factor pretty much completely. 15 and 10, 5 and 3, 5 and 2. So what are we going to have a pair of, Maya? Pair of 5s come out, and what stays inside? The 23. It's a 2 and a 3, right? Doesn't that make 23?
32.
Oh, it's a 32. I'm sorry. So we get 5 square root of 6 here. Any questions about that one? That's pretty easy, right? All right, so here's why we're doing these. We're actually not going to use the geometric mean right now. I just want to kind of refresh you on that. But what we are going to use is the arithmetic mean, going into the new stuff. Who can tell me how we find the coordinate of the point halfway between A and B? So we're going to say that AB is a line segment. We want to find the coordinate of the midpoint of that line segment. How do we do that? Counted them off. And somebody be specific. Tell me what you did. Tiffany?
I did 33 minus 9.
Okay.
And then I got 24.
And what did that, in this picture here, what does the 24 represent?
The distance between 9 and 33.
Okay, good. So what Tiffany did to start with is she found this distance here was 33 minus 9, which is 24. That's the distance between those 2 points. That is going to be useful here. What else? Tiffany?
I did 24 divided by 2 to get 12.
Okay. So if we find, half of 24, 24 divided by 2 is 12. And what does that tell you, Tiffany?
Well, I don't know how to explain it, but I did 9 plus 12 to get 21.
Okay, so I'll explain it for you. Half of 24 is half of the distance from A to B, right? So if we want to find the number that's halfway between A and B, we add half of that distance and we get to the halfway point. So if we're going from 9 to 33, halfway is going to be 12 units past the 9. So we can add 12 here to get 21 wherever the midpoint is. Actually, I'm going to write this somewhere else here so I don't get it confused on my grid. So we'll do 9 plus 12 equals 21. And this right here is actually the answer to what I was looking for there. Okay, that is the coordinate. The coordinate is just the location of the point halfway between A and B. Now, it's not all that I asked you to do. So I'm going to ask this now. Did anybody do anything else? First of all, did anybody find the 21 a different way? Allison, what'd you do?
I did 9 plus 33 divided by 2.
Okay. And when you do that, what are you actually doing? You're finding the...
Algebraic mean.
Yeah. So if you do 9 plus 33 divided by 2, you're finding the algebraic mean, and you're going to get, I'm just going to draw an arrow here, the same thing, right? So by finding the average of the two numbers, you're actually finding the number that's halfway in between, which is going to be the coordinate of the midpoint. Okay, so that would be another way to find the 21. A slightly simpler way, it's one step instead of 3 steps, but both ways work. What else could we do in this picture here? Actually, let me ask this question. What is the scale on the number line? Who can first explain to me what I mean by scale? Allie?
It's like the distance between one number to the next.
Yeah. So the scale on a number line is the distance from one tick mark to the next tick mark. So the scale on this number line is the distance between those two. Or really the distance between any two. It could be this distance right here also. Allie, how could we find that?
I did 33 minus 9 equals 24, and then 24 divided by 6 because there's 6 spaces.
Okay, good. So we'll count the number of spaces here. There's 1, 2, 3, 4, 5, and 6 spaces between the 9 and the 33, between A and B. So if we take the distance that Tiffany found earlier, that 24, and divide it by 6, that's going to give us what, Allie?
Plus 4.
Yeah, and actually I'll just write it down here. We'll take the distance divided by the number of spaces, and we get a scale of 4. So that means that the distance between each of those spaces is going to be 4. Now, knowing that, what else could I do on the number line? I didn't ask you to do this, but I'm guessing that a lot of you did still. Yeah, we could label each of those tick marks now with the value. So Tiffany, starting at A, what are we going to get? What comes after the 9?
13.
Then what?
17, and 21, and 25, and 29.
And having that on there now, we can see that the midpoint is going to be right there, because we know the midpoint is at 21. I'm not going to take a whole lot of time to go through this, because we're going to hit this with some examples here. But one of the important things about this that you need to understand is there are a lot of ways to approach this problem. We could find the scale a few different ways. We can find the midpoint a few different ways. We can figure out what each of those individual numbers is a few different ways. And each way, as long as it's a valid way, is perfectly acceptable. So if you found those same things, found that 21 is the midpoint, the 4 is the scale, those numbers on the tick marks in a different way, as long as that way is valid, it's going to work. Okay? Now, you don't want to come up with a way that will do it with this situation, but it won't work with a different situation. You want to come up with methods that will work for any kind of situation. And we're going to kind of do that with that halfway point, the midpoint. Any questions about this? All right, let's do some examples then. Actually, let's not do the examples yet. I want to talk about some stuff first. You guys remember Euclid? Who was he? Some guy that did something, probably something to do with math, right? Since we're in a math class.
Something to do with geometry.
How many people kind of vaguely remember talking about a guy named Euclid early in the school year?
I remember the name.
Okay, cool. Does anybody have any idea what we were talking about when we were talking about Euclid? Raven?
I know it was him and another man, I think, and one man had like the plane geometry and the other man had the other kind of geometry.
Okay, and that's exactly what we're going to talk about today. So Euclid kind of developed one type of geometry, in fact, the kind of geometry we've been doing all school year, and then some other guy that we're going to talk about in a minute developed a completely, I shouldn't say completely, a very different kind of geometry that can do very different things than Euclidean geometry and is useful in different ways. What else did we talk about when we talked about Euclid? Not kind of, sort of, yeah. So the first time I talked to you about Euclid was when I talked to you about Euclid's axioms. You guys remember the axioms, or what an axiom is? We actually call them postulates. What are the postulates?
The things on the board?
The pink ones, right? Or the salmon or orange or whatever color you want to call those. Okay. Those are the postulates. So Euclid was the first guy that we know of, at least, to kind of formalize math. And he did it with geometry as opposed to other branches of math, because geometry was kind of the predominant... It was predominantly what math was used for, was to do geometry stuff. And he formalized it. He came up with these 5 axioms that basically said between any 2 points is a line, and you can extend the line indefinitely. All right angles are congruent. These sounding familiar to you? He also had that really long one that said that if a line falling on 2 other lines forms angles that are less than 2 right angles, then they intersect on that side and stuff like that. That was Euclid's 5th axiom. That was called the parallel postulate. But he came up with those 5 axioms, and then everything else in geometry was based on those 5. He also had to include some definitions, which we have on which arrows? The green ones. So we combine the axioms with the definitions, and we start getting
the yellows,
which are theorems. Okay, and all those theorems are kind of the big ideas in geometry, the stuff that we built from the definitions and postulates. Okay, so Euclid's geometry was based on very simple ideas, and then he grew the complexity of the geometry out of that. So he gave us stuff like mathematical proof. Don't you love him? He was the first mathematician, like I said, that we know of, that really formalized mathematical proof. And in Euclid's geometry, called Euclidean Geometry, it's a crazy name, right? The important thing was the relationships between shapes. So the distances between points, the lengths of segments, the shape and size of things. One thing that didn't matter or doesn't matter in Euclid's geometry is location, where something is. these two triangles here, we showed how we can prove triangles are congruent to each other in a lot of different ways. None of those ways required that the triangles be close to each other, touching each other, far away from each other. The locations and positions didn't matter. So we can twist it, we can spin it, we can translate it, we can do all kinds of isometric translations and movements with it, and it doesn't change the triangle. Okay? You guys remember what the basic idea of congruence was that we talked about at the beginning of the year? We first started talking about congruent shapes. How did we define it? How did we define congruent shapes? Tiffany? Nope. This may be a little tricky because we haven't really talked about this idea of congruence for a long time, but it's the basis of all congruence. You remember? No.
Wait, did you say congruent shape?
Congruent shapes. So it doesn't have to be triangles, it doesn't have to be quadrilaterals, it doesn't have to be any specific kind of shape, it could be a squiggle. How could we show that one squiggle is congruent to another squiggle? Raven?
By the angle?
No. Because a squiggle wouldn't really have angles, would it? William, you remember?
Maya.
Maya does? Maya? Yes. So we said it a little more formal than that, but the idea is if we can take one shape and lay it on top of the other and it's exactly the same, then they're congruent. And we use the idea of isometries. And isometry is a movement that preserves the measurement. You guys remember doing the isometric drawings where measurements are preserved? So an isometry was a translation, a rotation, or a reflection. So you can slide something, you can flip something, or you can spin something. And as long as you're not changing the shape, if you can change it into the other one, then they're congruent by doing those three things. Okay, that was Euclid's idea of congruence. The location of something didn't matter. And that's the important thing. It's just the relationships between points. Now, what we're going to talk about today is a type of geometry that was developed by a French guy named Rene Descartes from I believe it was the 1600s, maybe late 1500s. First of all, the name Rene is masculine. Anybody taking French in here? Nobody in here taking French?
Masculine, what does that mean?
William, how do you know that's the masculine Rene, not the feminine?
The E/ on the
Apostrophe?
It's because of where the accent is, right? You remember that? No? Didn't you say you're taking French?
Yeah.
Do I need to talk to Miss York and let her know that you don't know
Same way
this?
for me in Spanish.
Isn't this something you're supposed to know? No? Okay. Anyway, he was French. He is actually more well known for his work in philosophy than he is for his work in math, even though his work in math is probably more significant to things that happen today. But in philosophy, he said this. This is not French. This is actually Latin. Cogito ergo sum. Anybody have any idea what that means?
Cogito ergo sum. I'm
Close.
gonna guess. If you take one, you get another.
Allie got one of them right. Ergo means therefore. This means I think, therefore I am. Have you ever heard that?
It's like a Dr. Seuss book.
Do you know why he said that? Anybody have any idea why he said that? This is a philosophy thing now. This doesn't have anything to do with geometry. This is what he's best known for in the modern world. He said this because one of the main philosophical questions at the time was, do we actually exist? How do I know that I exist?
You're alive.
Could you breathe?
Well,
Feel?
but
You can touch yourself.
guys, it was a very interesting philosophical question. Anybody ever seen the movie The Matrix?
Yeah.
Yeah. If you've seen the movie The Matrix, you can kind of, if you know the premise of that movie, you can kind of see how deep this kind of thing can go. Where
So are we alive?
well, so what he said was, I must exist because I'm thinking about my existence. So the fact that I can think about it means that I exist. Now, he didn't say I exist as I perceive myself. He just said I know that I exist in some way. So it was actually, it seems like a very simple idea, but it was kind of a big breakthrough. I think Dante was one that said, well, I'm breathing air. And I'm glad you said that, because one of the lines in the movie The Matrix, Morpheus says to Neo, you think that's air that you're breathing? And, yeah. Anyway, good talk. Here's what he's known for in the math world. In the math world, he developed this thing. What's this thing called?
Coordinate plane.
The coordinate plane. Now, almost everything we do in modern math is done on the coordinate plane, or at least in modern geometry. If you take a calculus class, it's usually, or a pre-calculus class, it's analytic geometry and calculus. Analytic geometry is geometry on the coordinate plane. Okay? So Rene Descartes came up with the coordinate plane. It's actually called the Cartesian coordinate plane, named after Rene Descartes. Anybody ever heard that term, Cartesian? Maybe, maybe not. So the Cartesian coordinate plane is named after this guy, this philosopher and mathematician, Rene Descartes. When he invented the coordinate plane, when he first started using it, he only used the first quadrant. He didn't use it as we do today. Where's the first quadrant in the coordinate plane?
Left.
Top right.
The top right. The first quadrant is where everything is positive. So he only used positive numbers in his coordinate plane, and it limited what he could do with it quite a bit, but it still allowed him to solve a lot of mathematical problems of his time in a very simple way compared to what other mathematicians were trying to do without the coordinate plane. And if I throw these same triangles up here that we had earlier, all of a sudden these triangles not only have relationships between each other, but they also have what? They have coordinates. They have a location. So we can talk about the location of point A as an ordered pair. You guys remember what an ordered pair is? Yeah, what would be the location of point A? Who can tell me? Point A right here. What? -1, 2. So the coordinates of point A here would be, maybe I'll write it down here, -1, probably should use a color that you can see, -1, 2, and that's not an ordered pair the way I have it written. What am I missing? The parentheses, right? We'll get into that more later, but that right there now gives us a location of A. What Descartes did was he allowed us to take everything that we did in Euclidean geometry and continue to do that, but also look at the relationships of things based on their locations, look at the relationships of lines based on their slopes and equations, and look at the relationships of curves, which we're not really going to do in here. We will a little bit maybe, but we can look at a lot of new stuff using the coordinate plane. Okay. So let's talk about it real quick here. Some terminology. What's an axis? What lines? There's a bunch of lines up there. The green ones, right? So the axes is plural for axis. The axes are what? What do we call them?
X and Y.
There's an x-axis and a y-axis. Which axis is this one?
Y.
That's the y-axis. And which axis is this? That's the x-axis. Also sometimes known as the... Anybody know which one's dependent and independent?
Dependent is down. No, is that right?
Dependent is the vertical one. So the y-axis is the dependent axis. The independent axis is the x-axis. And we use those terms because, like, if you're in chemistry class or physics class and you're graphing something, you're usually not using x and y, but you're using some other variables that are appropriate for whatever you're graphing. So in this class, we'll be using x and y, but those coordinates, or those axes, could be a time coordinate, or a distance coordinate, or a pH coordinate, an acidity coordinate. So it could represent really anything. It doesn't have to be x and y. What's a quadrant?
One of the four corners.
It's not just the corners.
One of the four.
Yeah, Allie used the word section, or you could look at it as a region. It's the four regions of the coordinate plane that are divided by the axes. Yes. So the four coordinates, the first one is the top right one, and the top right coordinate is everything above the x-axis and to the right of the y-axis. The second coordinate is everything to the left of the y-axis and above the x-axis. And those go around. And we're not really going to talk about the quadrants much, so I'm not going to spend much time here. What's an ordered pair? Okay, they're coordinates of a point. So it's a representation of a point written how? What does an ordered pair look like?
1, 2.
Okay, I like that you used x and y. Was that you, Maya?
Yes.
Does x have to come first?
Yes.
How do we know that x comes first? Yeah, the easiest way to remember it is that x comes before y in the alphabet. Remember, it's an ordered pair, so it always needs to be in order, in a correct order. If we start flipping things around, we don't know if x is first or y is first, then it's really pretty much pointless. It always has to have a comma between the x value and the y value, and it always has parentheses around them, right? Okay, all stuff that you already knew, right? Okay, how about this? Anybody know what a lattice point is? Nope, doesn't have anything to do with lettuce. Let me throw some points up here.
Oh, is it like when the point reaches in the middle?
On the points that's not in the it's not in the line.
Okay, so 3 of these points are on lattice points, 3 of them are not on lattice points. Which 3 do you think are on lattice points? Raise your hand if you think you know. Jake? No. William?
A, C, F.
Why?
Because they're on the thing.
I don't know what things are.
The lattice points, man.
Okay, they're on the grid lines. Grid lines would be an appropriate word to use there. So the important thing about lattice points, they do a few things for us. First of all, a lattice point is a point that is at the intersection of 2 grid lines. So A is a lattice point because it is where a vertical grid line crosses a horizontal grid line. B is not on a lattice point because even though it's on a horizontal grid line, it is not on a vertical grid line. And same thing here with D and E. You can see why they're not lattice points. The thing about lattice points is we know more about them than we know about non-lattice points. We know the coordinates of, say, point F. What are the coordinates of point F? 3, 0. So the coordinates of point F would be 3, 0. We don't know the coordinates of, say, point B. I know that the y-coordinate is 1. I don't know what the x-coordinate is. It's somewhere between 1 and 2. It looks like it might be about 2/5 of the way between them. Maybe. I don't know. So there's an unknown there. So lattice points are important because it gives us information that we don't have about other stuff. Okay, does that make sense? Okay. So these are the 2 types of geometries we deal with in this class. We've been doing Euclidean geometry all year. We're moving into analytic geometry. I was going to kind of compare them at this point, but we're running out of time, and I do want to get a couple examples done here. So let's move on. First example. I want to find the midpoint of line segment AB. Now, there's not really a line segment drawn on here, but points A and B are points on a number line. I want to know what is the coordinate or the value of the point halfway between A and B, or the midpoint. How do we do that? This is pretty easy. I think it was Allison that told us how to do this in the opener. Austin, what do we do?
3 plus 7 equals 10. And then you do 10 divided by 2.
Okay, so we're gonna do 3 plus 7 and then divide by 2. And what we're really doing here is finding the average. We're finding the arithmetic mean, or the average of the 2 numbers, to find the midpoint. And in this case, we get 5. It's easy enough, right?
Yes, sir.
Don't forget to show me how you're getting answers. If you just write down 5, that won't be good enough. How about the second one here? How do we find the average of -3 and 17?
Same thing.
Be more specific. It's not the same thing. The same thing would be 3 plus 7 divided by 2. We're not going to do that, I hope.
3 plus 17 divided by 2.
What's negative 3 plus 17?
Negative, or 14.
14 divided by 2 is?
7.
That's easy enough, right? So this is really simple. On a number line, if we want to find the number that's halfway between two numbers, or the point that's halfway between 2 points, you can just take the average. Okay? Another way to do it would be to find the distance between them, divide that by 2 and find half the distance, add that onto the starting point, and that'll give you the midpoint also. It's a little bit more work, but it's also very useful. That method is useful also if you want to find, for example, a number that's a third of the way between two numbers, or 2/5 of the way between two numbers. We're not going to do that, though. You don't need to worry about doing that. Okay, in the next example, I give you the midpoint and one of the endpoints. I want to know what the other endpoint is. Now, let's use that formula first. There's a quicker way to do it, but let's use the formula first. You want to help me with it?
Wait, use the divided by 2?
Let me write the formula that I'm using up top here. So the midpoint is equal to the coordinate at point A plus the coordinate at point B divided by 2. Alright? So we're going to use that formula and plug in what we knew. No, go ahead, Raven.
I kind of did a guessing check. I did 7 plus 4 because it's 3. It's 3 to go to 7.
Let's use the formula.
Well, I checked it with the
Let's use the formula. Who can plug in what we know into that formula? Allison?
7 equals 3 plus b divided by 2.
Okay, good. So 7 is the midpoint. We're putting that in for m here. Equals 3, that's the value of the coordinate at A, plus b, we don't know that one, that's the one we're trying to find, divided by 2. And then what do we do to solve that? Allison? Thanks, William.
You multiply both sides by 2.
Multiply both sides by 2, so we get 14 equals 3 plus b. And then what? By doing what? Subtract 3 from both sides and we get 11 equals b. So the coordinate at b is going to be 11. Now, Raven did it a different way, and I actually like the way Raven did it better. I just wanted to show that we can use that same formula to do this. However, remember, 7 is the average of 3 and the other number, right? It's the arithmetic mean, right?
Right.
What do you remember about arithmetic means and arithmetic sequences? Come on, it was less than an hour ago. You can't complain that we did it so long ago that you don't remember anymore. Okay, so in an arithmetic sequence, you add the same thing over and over again, or subtract, right? And an arithmetic mean is the number between two other numbers in an arithmetic sequence. Well, I know that 3 and 7 and whatever is going to go in here for b, they form an arithmetic sequence because 7 is the average of 3 and b. So if I think about it that way, what do I add on to 3 to get 7? Add 4. So I know 3 plus 4 is 7. Oh, you can't read that at all, can you? Let's try this one. 3 plus 4 is 7. So we'll do 7 plus 4 and get 11. And that way is a lot easier and does essentially the same thing that we just did. Now, if it's some big crazy number and we don't really know what we add on to 3 to get 7, we don't know what we add on to this to get this, what could I do to find that number? Subtract it. Just do 7 minus 3 and that'll tell us what we add on. Let's go ahead and do that for this next one here. To figure out what I add on to negative 3 to get 17, I would do 17 minus what? Negative 3, which is 20. So that means I'm going to add 20 to get 17, and then I add 20 more to get b, which is 37. Okay, I know I'm cutting it pretty close here. I'm going to give you I'm going to give you one more thing here, and I want you to write this down before you go. Where it says midpoint formula. You do need to get this written down before you go because you're going to use it for your homework tonight.